Welcome to another mathology video. Today's mission is to make sense of Powell's pi paradox. Never heard of it? Trust me, it's a good one. Also, the main tools that I'll be using to resolve this paradox are some amazing bits of half-forgotten medieval mathematics discovered by Indian mathematicians more than 600 years ago. Lots to look forward to today. Okay, let me get straight into it and introduce to you Powell's pi paradox. I'm sure a lot of regular mathologerers will be familiar with this mathematical gem, a formula for pi built from the odd numbers without a circle anywhere inside. Pi over 4 is equal to 1 minus 1/3 plus 1/5 minus 1/7, etc. Absolutely beautiful. And the mathologer regulars will probably also remember that I've already presented a couple of stunning proofs of this formula in earlier videos. Today we'll do something totally different. Let's start by multiplying both sides of this identity by 4. Okay. Now we can use the infinite sum on the right to compute arbitrarily many digits of pi by adding more and more of the terms. Okay, so let's see what we get when we sum the first million terms. In particular, let's compare pi with that monster sum. Here are the first couple of digits of both numbers. 3.14159, both at the top and at the bottom, a perfect match. Great. What about the next digits? 2 at the top and 1 at the bottom. Close, but no cigar. And when you think about it, that's actually quite disappointing. We just added 1 million terms of our series, and all we get for our efforts is a measly 6 correct digits of pi. Is that the paradox? Well, this ultra-slow convergence is definitely a bit surprising, but it's not the paradox. To get to the paradox, let's look at the next pair of digits. Both 6. Must be a coincidence, right? Well, could be. Just choosing 2 digits randomly, there's a 1 in 10 chance that they will coincide. What about the next digits? Both 5. Interesting. Next, both 3. What's going on here? By now we'd expect those digits to be all over the place. Why do you still come out the same? Let's keep checking. 5, 5, 8, 8, 9, 9, 7, 7, 9, 9, 3, 3, 2, 2, 3, 3, 8, 8. All the same. That's amazing. I guess at this point nobody watching will still believe that this is a coincidence. Nevertheless, nothing lasts forever and things actually do go off the rails again at the next pair of digits. 4 and 7. And surely from now on there won't be many more of those coincidences, right? Well, would you bet your life on it? Let's see. Okay, yep, 1 and 6 different. However, before you gamble your life away, check this out. 2, 2, 6, 6, 4, 4, 3, 3, 3, 3, 8, 8, 3, 3, 2, 2, 7, 7, 9, 9. Seriously? And then? All different, okay. But there are more coincidences. And it's not just if we add 1 million terms that we get this paradoxical behavior. A billion terms, a trillion terms, same thing. Intrigued? I bet. This paradoxical property of pi was first discovered in 1983 by the maths teacher Martin Powell while he was playing around on a computer. Why had nobody noticed this earlier? That's a bit of a paradox in itself, given the prominence of our gem and the fact that people have been obsessing over digits of pi forever. Just to put things into perspective, in 1983, more than 16 million digits of pi were already known. Okay, now for the ancient Indian discoveries that will serve as the key to explaining Powell's pi paradox. These discoveries consist of some beautiful patterns hiding deep in our mathematical gem. I grew up knowing this identity as the Leibniz formula, named after Gottfried Wilhelm Leibniz, who discovered it in 1673. Well, at some point people realized that Leibniz was actually not the first to discover this formula. The Scottish mathematician James Gregory beat him to it a couple of years earlier. And so now some people refer to the series as the Gregory-Leibniz formula. But even that name is misleading. It turns out that this gem was already discovered by the Indian astronomer and mathematician Madhava of San gamagrāma at least 200 years before Leibniz and Gregory. No, seriously, 200 whooping years before Leibniz and Gregory. That's about 1400, still in the Middle Ages. And it took until quite recently for Western mathematicians to actually recognize and acknowledge this. Does this count as another paradox? Those of you in the know will ask, isn't Leibniz's formula usually proved using calculus? Then how did those ancient Indian mathematicians derive it? Well, they used calculus. Really? It turns out that Madhava and his disciples already discovered quite a few of the crown jewels of calculus, including some derivatives and integrals, and some really advanced calculus stuff that you only learn about at uni. For example, when you replace the ones in the numerators of our series by the powers of x like this, you get the famous power series expansion of the inverse of the tangent function. For example, I teach this stuff in first year calculus at Monash Uni here in Australia. Now, believe it or not, Madhava and his colleagues even knew this very fancy piece of calculus, hundreds of years before Leibniz and Newton and Gregory invented calculus. Madhava also knew the corresponding series for sine and cosine. There, that's the series for sine, and that's the one for cosine. All right, now back to our jam. Madhava also discovered some beautiful hidden patterns in the series that were largely overlooked in the West until fairly recently. These patterns allowed him to speed up the slow convergence of the series on the right in a spectacular way. And it's these patterns that we'll use to explain the pi paradox. Okay, what are those mysterious patterns hiding in our series? Well, let's focus on the obvious patterns first. What we've got there on the right is a so-called alternating series. Plus, minus, the plus and the minus are alternating, taking turns. That's one easy pattern. And then, of course, there's the fact that the denominators are just the odd numbers. Now, let's go for it and use the sum on the right to approximate pi. Hands on. Okay, so the whole thing times 4 again, like before. Okay, so just fix it up like that. Now, roll in the number line. There's pi. There's pi, there's pi. Perfect. Now, what does the first term of our series tell us about pi? Pi is approximately equal to 4. Cool. Throw in the second term, minus 4 over 3. Okay, third term, and so on. And there. Okay, so adding the first 5 terms gives 3.34. That's better than 4, but 3.34 is still pretty pathetic. In fact, as I already mentioned earlier, although the infinite series on the right side of our pi formula definitely sums to pi, it does so ridiculously slowly and is effectively useless for obtaining decent approximations. So, Madhava's formula is beautiful but useless? Well, let's have another close look at what happens when we sum the series. There. First term. Here we overshoot pi. Second term. Here we undershoot pi. Next. Overshoot, and so on. Stopping the adding and subtracting at some point gives an approximation of pi. Yes, but have a closer look. Let's say we're here, and the plan is to stop after adding one more term. Okay, well, doesn't it look like we would end up much, much closer to pi if we only added half of that final term? Like so. Really much closer to the pi line than going all the way. Or what about here? Go halfway, again, better than all the way. Okay, so if we're after a really good approximation, it seems like we can do much, much better by choosing the last number we add in a smart way. And adding or subtracting half the final term seems pretty smart. But is there a way to even be smarter? Yes, there is. To chase it down, we'll look for a pattern in the difference between those partial sums of our series and the value of pi. That's these differences here. There, there, got it? It's one of these differences that we're trying to adjust as best as possible in the last step. But how can we possibly go pattern spotting in these differences between the partial sums and pi? After all, we don't know pi. Pi is what we want to calculate. Well, here's an idea. Remember, we entered the story in India around 1400, and by that time, the local mathematical hotshots already knew some damn good approximations for pi. Well, of course, there's Archimedes' super famous 22/7. You all know that one from school. 3.14, pretty good. But those Indian mathematicians already knew much better approximations of pi. Like, for example, the fantastic 355 divided by 113. 7 digits coincidence with pi? Not bad, huh? And now here's the key idea. Given one of our partial sums, forget about comparing it to pi and instead look at the difference between our partial sum and 355 over 113. We then hope that whatever patterns there are, these patterns will still show up when we use 355 divided by 113 instead of pi. Okay, so let's calculate the differences between our partial sums and 355 divided by 113. Here's the first difference in numbers. The first difference pans out to be this fraction, second difference, third difference, and so on. On to the pattern spotting. Can you see any pattern in those fractions? No? Well, not easy, but don't be too fixated on spotting an exact number pattern. Anything? Still no? Well, here's an easy one. In all those fractions, the number at the bottom is larger than the number at the top, right? There, 113 at the bottom is larger than 97 at the top, 339 is greater than 161, and so on. Not impressed? No, I didn't think you would be. But there's more. How much larger are the bottom numbers than the top numbers? Let's see. Well, roughly, the number at the bottom is equal to the one at the top plus a little bit. Here, the bottom number is about 2 times the number at the top. Next. Here, the bottom number is about 3 times the number at the top. Next. 4 times. Looks like there may be some pattern here. So the bottom is equal to the top number and a bit. To figure out how bitty that extra bit is, divide both the top and the bottom by the top, like this. Overall, still the same number, of course, but on top there is now a 1. And at the bottom we get 1 and the bitty bit we are after. There. Repeat for the next fraction. So divide the top and the bottom by the top. 1 on top and the 2 and a bit at the bottom, etc. 1, 2, 3, 4, 5. Does this pattern continue? Yep, this pattern continues forever and ever after. What does this mean? Well, take, for example, the sum of the first 4 terms of our series. Then to improve this pathetic approximation of pi, we can simply add 1/4. In the case of 5 terms, we minus a 1/5. In the case of 6 terms, we add a 1/6. Let's check how much better we're doing by using this correction term. There, the first 6 terms add to 2.97. Now add 1/6, 3.14. Much better. Now the first time 3.14 comes up in the partial sum of the original series is as we add the 121st term. Let's compare this to the adjusted sum. 7 digits compared to 3. Much better. But the ancient Indian mathematicians didn't stop there. They then had a closer look at the plus a bit fractions. 16 over 97, 17 over 161, and so on. Let's zoom in on the first fraction. Go on autopilot. Then 1 on top, sort out the bottom, repeat for everything inside. Now pattern spotting. Let's have a close look at the new integer parts. There. 6, 9, 13, 16, 20, 24. There's definitely something there, right? These numbers are a little wonky at the start, but then they are all multiples of 4. In fact, it turns out that after the first 3 blue numbers, the multiples of 4 pattern continues perfectly, forever. So after 16, 20 and 24, it's 28, then 32, 36, 40 and so on. And this suggests that we'll get even better approximations for pi if we choose the correction term to include these multiples of 4, like this. There and there. And here are the 3 different approximations we've got so far. On top, just the sum of the first 6 terms. In the middle, using 1/6 as a correction term. And at the bottom, using our new refined correction term. Not bad, huh? And here, the same for 121 terms. Again, the differences in the number of correct digits is very impressive. Now, in general, if we are adding n terms, the correction term is this. 1 over n plus 1 over 4n. What's next for our Indian mathematicians and us? Is there next? Of course, look at the remaining bitty fractions and try to discern a pattern. I'm going to skip the details. Let me just say that the Indian mathematicians were able to discover one more refinement of the correction term. It looks like this. And here's the approximation of pi that we get using the super duper correction term. Again, a very impressive improvement. In total, we've gone up from a 3-digit agreement with pi to 15 digits. Anyway, beyond this, the Indian mathematicians couldn't discern any more patterns, and so their part of the story ends here. Well, almost. But before I talk about the almost, let me now use these correction terms to explain Powell's pi paradox. Remember this picture here? These are the first 69 digits of pi at the top, and at the bottom the corresponding 69 digits of the sum of the first 1 million terms of the Madhava series. To start with, let me explain where the first discrepancy comes from. The approximation that corresponds to the first correction term 1 over n is much better than the millionth partial sum at the bottom, and actually coincides in all the visible digits with pi at the top. And what's the difference between these two numbers? Well, that's just the correction term 1 over n. And since n is 1 million, the difference is 1 millionth. 0.000001 zeros and then the 1. And this explains the first discrepancy between the partial sum and pi in the highlighted digits. In other words, for those first couple of digits visible up there, the partial sum coincides with the smack-on corrected sum except for this one highlighted digit. Not bad. What about the other discrepancies? Well, the digits at the top are those of pi. At the same time, they are also the digits of our very best approximation. The second number at the bottom is still our monstrous millionth partial sum. Now let's calculate the difference by plugging n equal to 1 million into our correction term. That's the correction term. On closer inspection, you see a bunch of strings of zeros and nines separated by some other strings of digits. Roughly, those strings of zeros and nines coincide with the regions of coincidence between pi and our millionth partial sum. And of course, these regions come from our super approximation of pi that is identical to pi within this range. I'm not going to dwell on the details. I think it's clear enough what's going on here. But here are a couple of observations. First, for many different types of numbers, like the powers of 10, the associate corrections will all have this 0-9 structure. Second, it's clear that, as before, strings of zeros should mostly correspond to regions of coincidence. Also, strings of nines are not that different from strings of zeros, since they are really just strings of zeros in disguise. What do I mean by this? Well, our 0-9 correction difference is equal to the difference of these two numbers. Right? Now focusing on the first string of nines, this string is really just the difference of this red-blue string on top, there, that one, minus the one at the bottom. Okay, so when we see a string of nines, we also expect about as many digits of coincidence, plus some possible differences at the beginning, at the end of the string. Anyway, overall, I hope it's clear enough for you to see what's going on. I should also mention that if you actually zoom further out, it turns out that Madhava's third correction term fails to give a complete explanation of the remaining few coincidences of the millionth sum and pi. However, it turns out that there is a fourth correction term, which Madhava missed. And this fourth correction term takes care of these remaining coincidences for the millionth sum. Here's that fourth correction term. Okay, well, whatever. In fact, there is an infinite sequence of these correction terms. How did Madhava miss these other correction terms? Well, remember, we were working with 355 divided by 113. That's just an approximation of pi, instead of with pi itself. And so it's not surprising that we will no longer pick up further patterns from some point on. Of course, Madhava could have used his supercorrection term to come up with a better approximation than 355 divided by 113, and then use that refined approximation instead of 355 divided by 113 in everything he did, in the hope that more of the true patterns will become apparent. And that would have worked, but of course it would have been very hard to put into action in 1400, without a computer or much of anything except his brilliant brain. Anyway, if you're interested in more details, I've put a bit of a discussion of the nitty-gritty bits, plus links to relevant papers in the description of this video. A very nice explanation, don't you think? And a good place to stop. But before I call it a day, I should say a little bit more about those medieval Indian mathematicians and their achievements. As I said, These guys definitely did discover a lot of deep calculus-related mathematics ages before their Western counterparts, and they deserve a lot more credit for what they did and how they did it. Of course, as with all things dating back that far, quite a few of the original records have been lost. In particular, there are no surviving mathematical texts by Madhava himself, only some texts on astronomy. What we do know about his mathematical discoveries is from later commentaries written by other members of his school in the 2 centuries following Madhava. What's particularly interesting for mathematicians like myself are not just the results but also the proofs. And Madhava and his disciples definitely cared about proving things properly. And essentially complete proofs, even by today's standards, can be found in their manuscripts. For example, the known Indian proof of Madhava's formula up there anticipates the modern slick integral-based proof. Truly amazing. In terms of how exactly Madhava discovered his 3 correction terms, we're not absolutely sure. In fact, I've based the line of reasoning that I presented to you today on some reconstructions by maths historians. Also, we do not know to what extent Madhava had proofs that his correction terms are valid forever and ever after. The first documented fairly involved proofs are part of Western post-Newton and Leibniz mathematics. Again, check out the description of this video for a lot more details of what is known today. Here's one final thing worth noting. Madhava also used his correction terms to come up with some new beautiful pi formulas, featuring very quickly converging series. For example, the first correction term translates into this spectacular formula for pi. And the second correction term corresponds to this pretty formula. How does one translate one of these correction terms into a new series? The explanation is actually quite simple. So to finish off, let me quickly show you how the translation works in the case of the first correction term. This one here. All right? Okay, so we start with our original infinite series. That one. Now calculate again the sequence of partial sums. Okay. Important observation. Notice that the terms of the infinite series below can be recovered from the sequence above. For example, the 4th term here is just the difference between the 4th and the 3rd elements of the sequence above, right? Blue minus green, the first 3 terms cancel, there, there, there. What remains is minus 4/7, the 4th term of our series at the bottom. Similarly with all the other terms. There, blue minus green equals orange, blue minus green equals orange, blue equals orange. Now, let's add the correction terms. This gives a new sequence of numbers. Now, what's the series that corresponds to this new sequence? Easy. As before, its terms are just differences between consecutive elements of the sequence. Like the 4th term here is just the difference between the 4th element and the 3rd element. Blue minus green, well, the same terms as before cancel, there, there, and there. And so the 4th term of the new series is this. Now, when an expert ponders the general formula for the n's difference a bit, they will notice that this term can be rewritten in this very beautiful, concise form. Not obvious, but at the same time, really just a bit of algebra. And then the other terms are calculated in the same way, there, and there, and there. In the same way, all correction terms can be turned into new infinite series formulas for pi. However, only the first 2 appear in those old Indian manuscripts. Why? Possibly because only in those first 2 the terms of the new series can be written in this surprisingly simple and beautiful way. Also, in those old Indian palm leaf manuscripts, all these formulas were not written in the concise mathematical language that we use today. There, they were all, believe it or not, they were all expressed in verse. And I guess you think twice before you note down anything ugly in verse. Anyway, that's it for today. I'll leave you with a detailed look at a page from one of those old manuscripts. See whether you can spot any X's.